What if everything we think we know about the birth of the universe is just the tip of the cosmic iceberg? For centuries, we've been taught that the Big Bang was the dramatic starting point of it all, a single, explosive moment that set space and time into motion. But what if the true story is far stranger, filled with twists and turns that even the brightest minds have overlooked? The universe's origins aren't just a straightforward tale of heat and expansion. They're a labyrinth of forgotten mysteries, bizarre anomalies, and jaw-dropping discoveries that rewrite the rules of reality itself. Imagine peering into the depths of space and stumbling upon clues that defy logic, cosmic echoes of events older than time, hidden forces shaping galaxies in ways we can't yet explain, and relics from epochs so ancient they predate the very fabric of existence. These aren't just abstract ideas, they're pieces of a puzzle that scientists are still scrambling to fit together. And the deeper we dig, the more we realize how much of the universe's history has been lost, ignored, or misunderstood. From ghostly particles that whisper secrets of the first seconds after creation to celestial oddities that shouldn't exist yet do, every revelation pulls us further down the rabbit hole. That's why we're diving into 25 of the most astonishing, mind-bending facts about how the universe really began. These aren't your textbook explanations or simplified sound bites. These are the untold stories, the cosmic enigmas that challenge everything we thought we knew. Some will make you question reality, others will leave you in awe of the sheer scale of what's hidden in the void. And by the end, you'll see the cosmos and our place in it in a whole new light, so buckle up. We're about to journey back to the very edges of time where the rules break down and the universe's greatest secrets are waiting to be uncovered. Right after the Big Bang, the universe wasn't just hot, it was hotter than anything we can possibly fathom. For a fraction of a second, temperatures soared past trillions of degrees, a scale so extreme it makes the core of our sun feel icy by comparison. This wasn't just a fleeting spike in heat, it was the furnace where reality itself was forged. At those mind-bending temperatures, energy was so intense that particles couldn't even hold their form. Protons, neutrons, and electrons, the building blocks of everything we know, were torn apart into a swirling soup of quarks and gluons, a state so chaotic scientists call it quark-gluon plasma. Think about holding a snowflake near a blast furnace. That's how delicate ordinary matter would have been in these conditions. The sheer violence of this heat didn't just create particles, it dictated the very rules of existence. For instance, the imbalance between matter and antimatter, why our universe is made of stuff rather than collapsing into nothing, might trace back to these first moments. Yet, this unimaginable inferno is often glossed over in pop science, treated as a footnote when it's really the universe's opening act. Here's what's even wilder. We've actually recreated traces of this primordial heat on Earth. Particle colliders like the Large Hadron Collider smash atoms together so forcefully that, for a split second, they generate temperatures millions of times hotter than the sun's core, giving us a glimpse into the universe's first microseconds. And yet, these experiments still only scratch the surface. The truth is, those first moments were so extreme that even our most advanced physics starts to break down trying to describe them. So why does this matter? Because that initial heat didn't just fade, it wrote the blueprint for everything. The way galaxies spin, the way stars ignite, even the fact that atoms exist at all stem from those trillions of degrees. It's like finding out the first brushstroke on a painting determined every color that followed, and yet we're only beginning to decode the secrets baked into that heat. What else might we discover hidden in those first unimaginable flames? The very idea of before the Big Bang might be a cosmic illusion, a trick of language that our brains can't quite escape. We're wired to think of time as a straight line, with events neatly marching from past to present to future. But what if time itself didn't exist until the universe burst into being? That's the staggering implication of Einstein's theory of relativity, which shows that space and time are woven together into a single fabric. The Big Bang didn't just create matter and energy, it spun the threads of time into existence. Asking what happened before is like asking what's north of the North Pole. The question collapses under its own weight. This isn't just philosophical wordplay. Cutting-edge physics like quantum gravity and loop quantum cosmology suggests time might have emerged from a state where our usual concepts of cause and effect simply didn't apply. Picture a frozen river suddenly melting and starting to flow. That's roughly how some theories describe the birth of time. In this view, the before was a timeless quantum foam, a seething chaos where space and time flickered in and out like static on a screen. There was no then, no earlier, just a roiling potential waiting to snap into the rhythm we now call reality. Even stranger, some models propose that the Big Bang wasn't a true beginning at all, but a bounce, a transition from a previous universe collapsing in on itself. In this scenario, time might cycle endlessly with no start or finish, only transformations. But here's the catch, these theories still require us to abandon the comforting idea of a linear timeline. Whether it's a quantum leap from nothingness or an eternal cycle, one thing's clear. Our everyday intuition about time is hopelessly inadequate for the cosmic deep past. So why does this matter? Because it forces us to rethink not just the origin of the universe, but the nature of existence itself. If time had a genesis, then creation isn't something that happened in time, it's the moment time began. That shifts the goalposts for every question we ask about our origins. It's not just that we lack answers, we might be asking the wrong questions altogether. And that's where the real mystery begins. The early universe wasn't just small, it was unimaginably tiny, squeezed into a space so minuscule it would make an atom look like a galaxy by comparison. Picture this, every star, planet, and galaxy we see today, all the vast emptiness between them, even the fabric of space itself, once crammed into a volume 1 billion times smaller than a single proton. That's not just compact, it's a density so extreme our brains have no reference point to comprehend it. At that scale, the laws of physics as we know them start to warp and twist, revealing a reality stranger than fiction. This mind-boggling compression is where inflation theory steps in, one of cosmology's most revolutionary ideas. In less time than it takes to blink, the universe didn't just expand, it exploded outward faster than the speed of light, doubling in size over and over again, like a runaway balloon inflating to cosmic proportions. But here's the twist, space itself was stretching, not matter moving through it, which skirts the usual speed limits. Think of it like dots on an inflating raisin, they're not zooming apart, the dough between them is swelling. In just a trillionth of a second, that subatomic speck became a sprawling cosmos, setting the stage for everything that followed. Why does this matter? Because that explosive growth left fingerprints we can still detect today. Tiny quantum fluctuations, random ripples in the primordial soup got stretched across the universe during inflation, eventually seeding the galaxies and voids we see now. Without that microscopic chaos, the cosmos might have been a featureless void. But here's what's truly humbling. Even our most advanced telescopes can't peer back past a certain point. The universe's earliest moments are shrouded in a fog of energy so intense that light couldn't travel freely until 380,000 years later. And yet, the mystery deepens. Some theories suggest the universe might not have been alone in that infinitesimal beginning. The same quantum physics that birthed our cosmos could have spawned countless others, each with its own rules, its own version of reality. Are we just one bubble in an endless froth of universes? The answer might lie hidden in those first fractions of a second, written in a language of energy we're only beginning to decode. One thing's certain, the smaller we look, the bigger the questions become. For nearly 400,000 years after the Big Bang, the universe wasn't just dark, it was utterly, blindingly opaque, a searing fog where light couldn't travel more than an inch before being swallowed by the chaos. This was the cosmic dark ages, but not in the way you might imagine. There were no stars, no galaxies, just an endless, churning ocean of plasma so dense and hot that photons, the particles of light, were trapped in a constant game of pinball, bouncing wildly between free electrons like a beam of sunlight struggling to pierce a thundercloud. The reason: temperature. In those first epochs, the universe was a scorching soup of ionized gas, where atoms couldn't even hold themselves together. Electrons, ripped away from their nuclei by the intense heat, turned space into a roiling sea of charged particles, and just like trying to see through a blizzard, light couldn't cut through that mess. Every photon emitted was immediately absorbed and re-emitted over and over, turning the cosmos into a glowing, impenetrable haze. But then something extraordinary happened. As the universe expanded, it cooled, slowly at first, then dramatically. Around the 380,000-year mark, temperatures finally dropped below 3,000 degrees, a threshold cold enough for electrons to snap into orbit around protons, forming the first stable hydrogen atoms. This moment, called recombination, was the universe's grand unveiling. Suddenly, without all those free electrons in the way, photons could travel unimpeded for the first time. Space went from opaque to transparent in what amounts to a cosmic blink of an eye. That ancient light, freed from its plasma prison, still fills the universe today. We know it as the cosmic microwave background, a faint, cold glow detectable in every direction, the oldest snapshot of the cosmos we'll ever have. It's like stumbling upon the fossilized echo of creation itself. But here's what's even wilder: that background radiation isn't perfectly uniform. Tiny fluctuations in its temperature, variations no larger than 100,000th of a degree, are the fingerprints of quantum ripples from the universe's infancy. Without those subtle imperfections, gravity wouldn't have had anything to grab onto, and galaxies, stars, and planets might never have formed at all. So the next time you look up at the night sky, remember, the darkness between the stars isn't empty. It's humming with the faint afterglow of that primordial dawn, a relic from the moment the universe first threw open its curtains and let the light shine through. The first stars in the universe weren't just bright, they were colossal, city-sized furnaces that made our sun look like a flickering candle. Born from the pure hydrogen and helium left over from the Big Bang, these behemoths, dubbed population 3 stars, could weigh in at hundreds of times the mass of our sun, burning at temperatures so extreme they would have outshone entire galaxies of modern stars. Without any heavier elements to slow their collapse, these titans formed in dense, pristine clouds of gas, growing to sizes we can scarcely imagine today. Their lives were as spectacular as they were brief. While a star like our sun might burn steadily for billions of years, population 3 stars lived fast and died young, exhausting their fuel in just a few million years, a cosmic blink of an eye. But their deaths were where the real magic happened. When these monsters finally ran out of fuel, they didn't just fade away. They detonated in supernovas of unimaginable violence, eruptions so powerful they briefly outshone the rest of the universe combined. And in those cataclysmic final moments, they did something extraordinary. They forged the first heavy elements in existence. The cores of these stars acted as cosmic factories, smashing atoms together under insane pressures and temperatures to create carbon, oxygen, iron, and even gold, elements that hadn't existed before. When the stars exploded, they scattered these newly minted elements across the cosmos, seeding the universe with the raw materials for planets, oceans, and eventually life itself. Without those first stars and their fiery deaths, the periodic table as we know it wouldn't exist. Here's the twist: we've never actually seen a population 3 star. They burned out so quickly and so long ago that even our most powerful telescopes can't spot them directly. Instead, we infer their existence from the chemical fingerprints they left behind, the telltale traces of primordial elements in the oldest galaxies we've observed. It's like finding ancient pottery shards and reconstructing the civilization that made them. But the hunt isn't over. Some astronomers believe a few of these relics might still linger in the most distant corners of the universe, hiding in plain sight, waiting to reveal secrets about the dawn of time. This raises an even bigger question. If those first stars were so massive, where are their remains? Some may have collapsed into black holes, seeding the early universe with the gravitational monsters that now lurk at the centers of galaxies. Others might have shattered so completely that not even their black holes survived. But one thing's certain, their legacy lives on. Every atom in your body, every piece of the world around you was forged in the hearts of stars. And the very first of those stars, they were the giants whose explosions wrote the recipe for everything that followed. If you could travel back to the universe's infancy and take a deep breath, if your lungs could somehow survive the scorching temperatures, you'd be hit with a bizarre, metallic scent, something like burnt toast mixed with the sharp tang of a welding torch. This isn't science fiction, it's chemistry writ large across the cosmos. In those first chaotic moments after the Big Bang, as the universe cooled enough for atoms to bond, simple molecules began to form, and their composition would have given space an odor utterly alien to our modern noses. The key player in this cosmic aroma, carbon monoxide, a molecule that pervaded the early universe alongside hydrogen and helium. When scientists simulate these conditions in labs, they find that the combination of these elements superheated, ionized, and then rapidly cooled produces compounds with a distinctly acrid, almost charred smell. Add in trace amounts of other early molecules like polycyclic aromatic hydrocarbons, which are also found in burnt food, and you've got a recipe for a universe that might have smelled like an overcooked diner breakfast. But here's what's even stranger. That scent wasn't just a fleeting quirk. It was a sign of the universe's first steps toward complexity. Those simple carbon-based molecules were the precursors to everything, the building blocks that would eventually form planets, organic compounds, and even the chemicals necessary for life. In a way, the universe's burnt toast phase was like the first faint notes of a symphony that would take billions of years to fully unfold, and the echoes of that era still linger. Astronomers have detected clouds of gas in distant galaxies rich with these same primordial molecules, their spectral signatures revealing compositions unchanged since the dawn of time. It's as if the cosmos bottled its own ancient perfume, preserving a whiff of its fiery youth. So next time you catch the scent of something burning, remember, you're smelling a faint echo of creation itself, a reminder that even the grandest cosmic story can have strangely relatable details. If we could peel back the layers of the universe like an onion, we'd find a hidden skeleton, a ghostly framework holding everything together. Dark matter, invisible and undetectable by ordinary means, is the unsung architect of the cosmos. While stars and galaxies dazzle us with their light, they're merely the glittering ornaments draped over this unseen scaffolding. Without dark matter's gravitational pull, the universe as we know it wouldn't exist. Here's the twist. Visible matter, the stuff we can see and touch, accounts for less than 5% of the universe's total mass. Yet galaxies spin faster and cling together more tightly than they should based on that meager amount. That discrepancy was the first clue that something was missing. Imagine building a skyscraper with only the glass windows and none of the steel beams. It would collapse instantly. Dark matter is that steel, the hidden structure providing the gravitational glue that keeps galaxies from flying apart. In the early universe, dark matter did the heavy lifting long before stars ignited. Tiny fluctuations in density, remnants of the Big Bang's quantum ripples, allowed dark matter to clump together under gravity's influence. These clumps became gravitational wells, pulling in hydrogen and helium gas like cosmic whirlpools. Only then, within these dark matter halos, could ordinary matter condense enough to ignite the first stars and seed galaxies. Without those invisible anchors, gas would have scattered across the void, and the night sky might have remained forever dark. But here's where intuition betrays us. We're wired to equate real with visible, so it's easy to assume galaxies formed from the bottom up, stars gathering into clusters, then galaxies, then superclusters. In reality, the opposite happened. Dark matter's gravitational blueprint came first, mapping out the large-scale structure of the cosmos. Galaxies didn't build themselves, they were born inside dark matter's embrace, like trees growing in the footprints of unseen giants. The evidence is everywhere. When astronomers map galaxy clusters, they find most of their mass resides in vast, diffuse halos extending far beyond the visible starlight. Some galaxies even move as if tugged by invisible hands, their trajectories revealing the presence of dark matter we can't see. And when light bends around massive objects, a phenomenon called gravitational lensing, the distortion often points to more mass than visible matter can explain. Yet for all its importance, dark matter remains a mystery. Is it a sea of undiscovered particles, a flaw in our understanding of gravity? Whatever the answer, one thing's certain: the universe's grand design was drawn in invisible ink, and we're only just beginning to trace its outlines. The next time you gaze at the Milky Way's shimmering band, remember, you're seeing just the faintest echo of a much deeper, darker story. Here's a mind-bender that flips everything you've ever heard about the Big Bang on its head. It wasn't an explosion in space, it was an explosion of space. Picture the universe not as a fireball erupting outward from some central point, but as every single speck of reality stretching simultaneously like dots on an inflating balloon. No matter where you stood in that primordial cosmos, you'd see everything rushing away from you because space itself was expanding everywhere at once. This distinction cracks open one of the most persistent misconceptions about the universe's birth. We're wired to imagine the Big Bang like a cosmic firework, a dazzling burst from a single location, scattering matter into the void. But the reality is far stranger. There was no outside for the explosion to expand into, no empty stage waiting to be filled. Instead, the entire universe, all of space and time, was compressed into an unimaginably hot, dense state, and then it simply got bigger. Everywhere at the same time. To grasp this, try the balloon analogy. Draw dots all over its surface. Those are galaxies. Now inflate it. Notice how every dot moves away from every other dot, with no single point acting as the center of the expansion. That's precisely how the universe works. Whether you're in the Milky Way or a galaxy billions of light years away, you'd observe the same thing. All distant galaxies receding, their light stretched redder as space itself carries them apart. But here's what makes this even wilder. The Big Bang didn't happen somewhere, it happened everywhere. The spot you're sitting in right now, that was part of the Big Bang. The farthest quasar we've ever detected, also part of the Big Bang. The entire observable universe was once crammed into a volume smaller than a marble. Not at some distant location, but right here and there and everywhere. When we look deep into space, we're not peering away from the explosion's origin. We're staring directly into its afterglow in all directions at once. This revelation reshapes how we think about the cosmos. There's no edge to the universe, no center, no before the Big Bang in any traditional sense. Space isn't expanding into anything, it's just becoming more space. And if that feels impossible to visualize, welcome to the club. Even physicists admit this bends everyday intuition to the breaking point. But the math doesn't lie. Those redshifted galaxies, the cosmic microwave background's uniformity, even the way clusters of matter are distributed, all of it points to a reality where here and there were once the same place, stretching together into the vast cosmic web we see today. So the next time someone says the Big Bang was an explosion in space, you'll know the truth runs deeper. It was the moment space itself woke up and started growing, a transformation so profound that, even 14 billion years later, we're still unraveling its mysteries. The seeds of every galaxy, every star, and even the vast cosmic voids between them weren't sown by some grand design. They were born from chaos, not the chaos of explosions or collisions, but the ghostly, subatomic jitters of quantum mechanics. In the first sliver of a second after the Big Bang, when the universe was smaller than a single atom, it wasn't perfectly smooth. Instead, it crackled with microscopic fluctuations, temporary bubbles of energy popping in and out of existence, a phenomenon so tiny it defies intuition. Yet these quantum ripples, magnified by the universe's explosive expansion, became the hidden blueprint for everything we see today. Imagine blowing up a balloon with tiny, invisible wrinkles on its surface. As the balloon inflates, those wrinkles stretch into vast mountains and valleys. That's precisely what happened during cosmic inflation, the universe's runaway growth spurt. Quantum fluctuations smaller than a trillionth of a centimeter were stretched across light years, imprinting the cosmos with faint density variations. These ripples didn't just fade away, they became gravitational anchors. Slightly denser regions pulled in more matter, while sparser areas emptied out, setting the stage for galaxies to cluster and voids to yawn between them. The proof is etched into the oldest light we can see, the cosmic microwave background. This afterglow from the universe's infancy appears nearly uniform, but ultra-sensitive telescopes reveal whisper-thin temperature differences. Some spots a hair warmer, others a fraction cooler. Those variations, just 1 part in 100,000, match the predictions of quantum physics perfectly. Warmer spots mark where matter was denser, cooler ones where it was thinner. It's as if we're staring at a fossilized snapshot of the universe's quantum skeleton, the scaffolding upon which all structure was hung. Here's what's truly staggering. Without those fluctuations, the cosmos might have remained a featureless sea of gas. Gravity needed something to work with, some imperfection to amplify. The same quantum randomness that makes subatomic particles flicker unpredictably also gave rise to the grand tapestry of galaxies. It turns out the universe's largest structures owe their existence to its smallest phenomena, a cosmic case of the butterfly effect where subatomic tremors birthed celestial giants. Yet the story doesn't end there. Those primordial ripples didn't just shape where galaxies would form, they also dictated how they'd move. Astronomers tracing the paths of thousands of galaxies find they're still flowing along rivers of dark matter, following gravitational currents set in motion by those first quantum whispers. Even now, 14 billion years later, the universe remembers its chaotic infancy. Every spiral arm, every cluster, every filament of the cosmic web is a direct descendant of those fleeting, microscopic ripples, proof that the universe's grandest structures were written in the language of the very small. Just when cosmologists thought they had the universe figured out, it threw them a curveball more baffling than anything they'd seen before. Back in the 1990s, 2 teams of astronomers set out to measure how fast the universe's expansion was slowing down. Conventional wisdom said gravity, the relentless pull of all matter in the cosmos, should be putting the brakes on that initial Big Bang momentum. Like a ball tossed upward, the universe's growth was expected to gradually lose steam, with galaxies coasting slower and slower over time. But the data told a radically different story. Instead of slowing, the universe's expansion was speeding up, as if some invisible foot had slammed down on the cosmic accelerator. This wasn't just unexpected, it upended decades of accepted science. The culprit, a mysterious force now known as dark energy, an enigmatic pressure woven into the fabric of space itself. Unlike gravity, which pulls things together, dark energy pushes, stretching the universe apart with a strength that grows as space expands. Think of it like rolling a ball downhill, only to watch it suddenly defy logic and roll faster uphill instead. Here's what makes this truly mind-bending. Dark energy isn't diluted as the universe grows. In fact, its influence becomes more dominant over time because it's tied to space itself. More space means more dark energy, creating a runaway effect where expansion begets even faster expansion. The evidence came from observing distant supernovas, the explosive deaths of white dwarf stars. These cosmic beacons have a predictable brightness, allowing astronomers to gauge their distance. But the supernovas were dimmer than they should have been, meaning they were farther away than expected, proof that the space between us and them had stretched more than anyone predicted. This discovery earned the researchers the Nobel Prize, but it left physics with a glaring hole. We still don't know what dark energy actually is. Some theories suggest it could be the cosmological constant, a kind of energy inherent to empty space, first proposed then rejected by Einstein. Others speculate it might be a dynamic field, like an invisible fluid filling the cosmos with repulsive gravity. The most unsettling possibility: dark energy's strength isn't constant. If it grows over time, it could eventually tear apart galaxies, stars, even atoms in a cataclysmic Big Rip. What's clear is that dark energy dominates the universe, making up about 68% of its total energy content. It's the reason distant galaxies are receding from us faster and faster, vanishing over a horizon we'll never cross. And here's the ultimate irony. If this acceleration continues, future civilizations might look up at an empty night sky, their telescopes revealing nothing but darkness as every other galaxy slips beyond the observable universe. The cosmos isn't just expanding, it's fleeing from itself, leaving us to ponder whether we're witnessing the first act of an eternal unraveling. One of the most humbling discoveries in modern astronomy didn't come from peering at bright, nearby galaxies. It came from staring into what looked like nothing. In 1995, the Hubble Space Telescope pointed its lens at a patch of sky no bigger than a grain of sand held at arm's length. A region so seemingly empty it was chosen precisely because it appeared devoid of stars. What came back wasn't darkness, but a kaleidoscope of light. Thousands of galaxies, some barely more than faint smudges, filled the frame, each one an island universe teeming with billions of stars. This single image, the Hubble Deep Field, shattered every assumption about the scale of the cosmos. Suddenly, the universe's known population of galaxies exploded. Before Hubble, astronomers estimated there might be around 100 billion galaxies in the observable universe. But as telescope technology advanced, so did the numbers. By studying the density of galaxies in that tiny sliver of sky and extrapolating across the entire cosmos, scientists realized the true count was staggeringly higher, somewhere north of 2 trillion galaxies, at least 20 times more than we'd imagined. That means if every star in our Milky Way represented an entire galaxy, there still wouldn't be enough stars to match the number of galaxies out there. Most of these galaxies aren't just distant, they're invisible to conventional telescopes. Some are so faint that their combined starlight wouldn't even equal the glow of a single flashlight on Earth seen from the moon. Others are buried in cosmic dust or shrouded by the glare of brighter neighbors. But the biggest reason we've missed so many: the universe has been playing a cruel trick with time and light. When we look at extremely distant galaxies, we're seeing them as they were billions of years ago. Many so young they hadn't yet formed the vibrant spirals and ellipticals we recognize today. Some might already be gone, their light only now reaching us long after their stars burned out. This revelation rewrites our understanding of cosmic evolution. If most galaxies are small, dim, and ancient, it suggests the early universe was a far busier place than we ever suspected. A crowded, chaotic nursery where galaxies formed, merged, and faded in unimaginable numbers. Some researchers now think our Milky Way could be the product of countless mergers with these ghostly dwarfs, their stars absorbed into our own like cosmic tributaries feeding a river. Yet for all we've learned, the Hubble Deep Field might just be the tip of the iceberg. New telescopes like JWST are now spotting galaxies even farther back in time, some so massive they shouldn't exist under current theories. Every time we push the limits of observation, the universe seems to say, "You haven't seen anything yet." And that's the most awe-inspiring part. 2 trillion galaxies isn't the final answer. It's just the closest guess we can make with the tools we have for now. The universe as we know it, with its towering galaxies, swirling nebulae, and the three-dimensional space we move through every day, might be nothing more than an elaborate illusion. One of the most radical theories in modern physics suggests reality could be a hologram, a vast, immersive projection encoded on a two-dimensional surface at the very edge of the cosmos. This isn't science fiction. It's the holographic principle, a concept born from the strange intersection of black hole physics and string theory that challenges everything we assume about existence. The idea first gained traction when physicists studying black holes hit a paradox. According to quantum mechanics, information can never be destroyed, yet black holes famously devour everything, even light. So where does the information go? The solution emerged when researchers realized a black hole's entropy, a measure of its hidden information, is proportional not to its volume but to the surface area of its event horizon. In other words, all the data describing what falls into a black hole might be smeared like a cosmic fingerprint across its boundary, preserved in 2 dimensions rather than 3. This hinted at a staggering possibility. If a black hole's interior can be fully described by information on its surface, could the same be true for the entire universe? String theorists took this further, proposing that our three-dimensional reality might be analogous to a movie screen. The images we see have depth and motion, but they're ultimately projected from flat, two-dimensional data. Similarly, the holographic principle suggests all the particles, forces, and even the fabric of space-time in our universe could be encoded on a distant, two-dimensional boundary, a surface we'll never see or interact with directly. The cosmos, then, wouldn't have 3 dimensions. It would simulate them like a shadow puppet casting the illusion of solid objects. Evidence for this is subtle but compelling. Certain calculations in quantum gravity, attempts to unify general relativity with quantum mechanics, work more cleanly when space is treated as 2-dimensional rather than 3. It's as if the math itself is hinting that the third dimension is emergent, a byproduct of deeper, flatter physics. Even the cosmic microwave background, the afterglow of the Big Bang, shows patterns that some researchers argue resemble holographic interference, like the pixelation of a projection stretched across the sky. The implications are dizzying. If the holographic principle holds, then free will, time, and even our sense of self might be secondary phenomena, side effects of a deeper, simpler reality playing out on some unimaginable surface. It would mean the universe is fundamentally an information system, with every event from supernovas to thoughts reducible to bits etched on a cosmic hard drive. And it raises an unsettling question. If we're living in a hologram, who or what is holding the projector? Yet for all its elegance, the holographic principle remains controversial. Not all physicists are convinced, and the math is so abstract that experimental proof is elusive. But whether it's ultimately true or not, the idea has already reshaped how we think about space, time, and the nature of reality itself. It's a reminder that the universe's greatest secrets might not lie in the vastness of space, but in the hidden codes written on its edges, codes we're only beginning to decipher. Time didn't tick the same way in the early universe as it does today. In fact, the first moments after the Big Bang unfolded in extreme slow motion from our modern perspective. Thanks to Einstein's theory of relativity, we know gravity and velocity don't just bend space, they warp time itself. Near a black hole or in the depths of a gravitational well, clocks tick slower compared to those in open space. Now imagine that effect cranked to unimaginable extremes. In the universe's first seconds, when all matter and energy were crushed into a space smaller than a proton, gravity was so intense that time itself stretched like taffy. What we now measure as a single second might have felt like an eternity back then. a dizzying realization that rewrites how we perceive the cosmos's birth. This isn't just theoretical. Particle collisions in accelerators like the Large Hadron Collider offer glimpses of these conditions. When atoms are smashed together at nearly light speed, time dilation becomes measurable. Unstable particles that should decay in nanoseconds suddenly persist far longer from our frame of reference. Translate that to the early universe, where densities and temperatures dwarf anything we can recreate, and time's slowdown becomes unavoidable. Those first 3 minutes, famously described by cosmologists. They might have stretched subjectively for eons in the universe's own warped time frame. The implications ripple outward. For instance, the cosmic microwave background, the oldest light we observe, was emitted about 380,000 years after the Big Bang. But thanks to time dilation, the processes leading up to that moment, like the formation of the first atoms, might have unfolded far more slowly from our vantage point than they did on the ground in that ultra-dense early cosmos. It's like watching a video of someone running in slow motion while they experience it at normal speed. Relativity also solves a paradox: how the universe could become so large and complex so quickly. From our perspective, inflation happened in a fraction of a second, but in the universe's own distorted timeline, the process might have had vastly more room to play out. This time-warping effect even influences how we detect ancient events today. Distant supernovas from the early cosmos appear to unfold slower than their modern counterparts, not because the explosions were different, but because the stretched space-time of the young universe delays their light's arrival like a cosmic echo. So the next time you hear about the Big Bang's first moments, remember, the universe's stopwatch wasn't just counting seconds. It was moving through molasses, caught in a gravitational grip so fierce that time itself struggled to keep up. And that's the real wonder. Even the most fundamental aspects of reality, like the passage of time, aren't fixed. They bend, twist, and breathe along with the cosmos, reminding us that the universe's origins weren't just a moment in time, but a reshaping of time itself. Helium-3, the universe's shyest isotope, might seem insignificant next to its more abundant cousin, helium-4. But this lightweight element, just a single neutron shy of normal helium, holds secrets that could rewrite our understanding of the cosmos's first moments. While helium-4 fills party balloons and makes voices squeaky, helium-3 is vanishingly rare, making up less than 1 in 10,000 helium atoms on Earth. Yet its scarcity is precisely what makes it so precious to scientists. This elusive isotope isn't just a cosmic afterthought. It's a fossil from the universe's nuclear dawn, a whisper left over from the inferno of nucleosynthesis in the Big Bang's first 3 minutes. Back then, the universe was a seething cauldron of protons and neutrons, too hot for stable atoms but just right for nuclear fusion. As temperatures cooled, those particles began clumping into the first atomic nuclei, mostly hydrogen, a dash of helium-4, and a mere sprinkle of helium-3. The delicate balance of these elements was dictated by the universe's density and temperature at the time, like a recipe scribbled in the language of particle physics. Helium-3's trace presence is one of the few direct lines we have to that primordial kitchen, a fingerprint lingering from before stars or galaxies even existed. But here's the puzzle: there's far less helium-3 in the cosmos than the Big Bang's equations predict. Some of it was undoubtedly destroyed in stars, fused into heavier elements over billions of years. Yet even accounting for that, the numbers don't quite add up. One theory suggests helium-3 might hide in plain sight, trapped in the atmospheres of gas giants like Jupiter or locked in the solar wind. Another proposes it's been stealthily absorbed by interstellar dust, clinging to grains in the cold voids between stars, the most tantalizing possibility. That undiscovered physics, perhaps particles or forces beyond our current models, altered the isotope's abundance in ways we haven't yet imagined. This isn't just academic curiosity. Helium-3's behavior under extreme conditions makes it a superstar in quantum research. When chilled to near absolute zero, it becomes a superfluid, defying gravity and climbing the walls of its container as if possessed. These bizarre properties might hold clues about the quantum nature of spacetime itself, linking the infinitesimal world of particles to the vast architecture of the cosmos. So the next time you hear about helium, remember, its rare isotope isn't just a scientific oddity. It's a cosmic detective carrying evidence from the universe's earliest crime scene. And until we crack its case, some of the Big Bang's best-kept secrets will remain just out of reach. If you could shrink the universe down to the size of a city, galaxies wouldn't be scattered randomly like disconnected islands. They'd form a sprawling, luminous subway map. This is the cosmic web, a network of thread-like filaments stretching hundreds of millions of light-years, with galaxies clustered like glittering stations at the intersections. These filaments aren't just empty lines, they're colossal rivers of dark matter and hydrogen gas, so vast that a single strand could take a beam of light billions of years to traverse. This isn't just structure, it's the universe's skeleton, the hidden framework that's dictated where every galaxy, star, and planet would eventually form. Simulations of the early universe reveal how this web emerged from chaos. Dark matter, invisible and indifferent to light, began clumping under gravity's pull, forming delicate tendrils in the primordial soup. Ordinary matter, the gas that would become stars, followed suit, flowing along these dark matter highways like water, finding the path of least resistance. Over eons, these filaments thickened, knots of gas collapsing into galaxies at their intersections. The result, a sponge-like structure where most of the universe's mass is concentrated in these threads, while the voids between them stretch for incomprehensible distances, nearly empty except for a few wandering stars exiled from their homes. What's staggering is the scale. A typical filament might be 10 million light-years across but stretch for 500 million light-years, long enough to loop around the Milky Way 100,000 times. And the gas within them, ISNT Chinese letter, it's a superheated plasma seething at temperatures of 10 million degrees or more. This intergalactic medium glows faintly in X-rays, a ghostly beacon that telescopes like Chandra have mapped, revealing filaments so delicate they'd vanish if you looked at them head-on, yet so massive they dictate the fate of entire galactic superclusters. Here's where it gets even wilder. The cosmic web isn't static. It's a living, evolving structure. Galaxies aren't just parked at intersections. They're in constant motion, surfing the gravitational currents of these filaments. Some are pulled toward dense nodes where they'll eventually collide and merge. Others drift along the strands like beads on a string, destined to orbit in the web's embrace for billions of years. Even the gas itself is recycled, blown out by supernovas, then drawn back into the filaments, ready to fuel new generations of stars. And yet, for all its grandeur, the cosmic web is fragile. Its structure depends on a precise balance between gravity's relentless pull and dark energy's accelerating push. As the universe expands, those filaments will stretch thinner, the voids between them growing ever larger. One day, far in the future, the web may fray entirely, its strands snapping like overstretched threads. But for now, it stands as the universe's most breathtaking artwork, a masterpiece woven from darkness and light whose patterns we're only beginning to trace. The universe might not just fade away quietly, it could be torn apart atom by atom in one of the most violent endings imaginable. While we often picture cosmic demise as a slow cooling or a dramatic collapse, the Big Rip offers a far more visceral finale. Dark energy, the same mysterious force accelerating the universe's expansion today, could become so overpowering that it doesn't just push galaxies apart, it shreds the very fabric of reality. Picture this, around 100 billion years from now, as dark energy's influence grows, galaxy clusters would first drift out of each other's view. Then individual galaxies would unravel, their stars scattered into the void, Next, solar systems would be ripped apart, planets torn from their suns. In the final, grisly moments, even atoms would be stretched to the breaking point, their nuclei unable to withstand the relentless stretching of space itself. The universe wouldn't just end, it would dissolve into a sea of disconnected particles, each forever isolated by the infinite expansion between them. This apocalyptic scenario hinges on a specific property of dark energy called its equation of state, essentially how its strength changes over time. If dark energy's repulsive force intensifies as space expands rather than remaining constant, it would trigger a runaway effect. The more the universe grows, the stronger dark energy becomes, creating a feedback loop that ends only when nothing bound by gravity or nuclear forces can survive. But the Big Rip isn't the only grim option on the table. For decades, scientists debated a big crunch, where gravity would eventually reverse the expansion, collapsing everything back into a singularity, a mirror image of the Big Bang. This scenario required a universe dense enough to overcome dark energy's push, but observations now suggest that's unlikely. Then there's heat death, the slowest and quietest end, where the universe expands forever, stars burn out, and matter decays into a featureless, lukewarm haze. No explosions, no drama, just entropy's inevitable victory. What makes the Big Rip uniquely terrifying is its inevitability if dark energy behaves a certain way. Unlike the heat death, which plays out over near eternity, the rip could happen relatively suddenly on cosmic timescales. And unlike the crunch, there's no rebirth, no cycle, or just irreversible disintegration. Yet here's the twist: we don't yet know which fate awaits us. Dark energy's nature remains one of physics' biggest unsolved puzzles. Future telescopes, like the Vera Rubin Observatory, aim to measure its properties with unprecedented precision, potentially ruling out or confirming the rip's nightmare scenario. Until then, the universe's ultimate destiny hangs in the balance, a reminder that even the mightiest structures are at the mercy of forces we're only beginning to understand. Every second, trillions of nearly invisible particles pass straight through your body without you ever noticing leftover relics from the universe's fiery birth called neutrinos. These ghostly wanderers outnumber atoms by billions to one, saturating every corner of the cosmos with their silent presence. Born in the nuclear inferno of the Big Bang and later forged in the hearts of stars and supernova, neutrinos barely interact with matter at all. A single neutrino could slice through a light year of solid lead without slowing down, making them the universe's ultimate escape artists. What makes neutrinos so elusive? They lack an electric charge and have almost no mass, so tiny that physicists once thought they might weigh nothing at all. This ethereal nature lets them stream unimpeded through planets, stars, and even you, like whispers in a hurricane. Yet despite their reluctance to mingle with ordinary matter, neutrinos play a starring role in some of the universe's most violent events. When a massive star collapses in a supernova, 99% of its energy isn't blasted outward as light. It's carried away by a tsunami of neutrinos. These particles surge through the dying star's outer layers like an unstoppable shockwave, helping trigger the explosion that seeds galaxies with heavy elements essential for life. The universe's neutrino background is even more ancient. Just 1 second after the Big Bang, the cosmos was so dense that even these phantom particles got briefly trapped in the chaos. As space expanded, they broke free, creating a cosmic neutrino background that still permeates everything a fossil from the universe's first breath. Unlike the cosmic microwave background, this neutrino echo is far colder and harder to detect, with particles now moving sluggishly at speeds comparable to a speeding car. Here's where the story takes a strange turn. Neutrinos might hold clues to one of physics' biggest mysteries: why the universe is made of matter at all. According to theory, the Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other instantly, yet here we are. Neutrinos, with their peculiar habit of shape shifting between three different flavors as they travel, could hint at undiscovered physics that tip the scales in matter's favor. If neutrinos and their antimatter counterparts behave even slightly differently, it might explain how a single extra matter particle survived for every billion annihilations, just enough to build galaxies, planets, and us. Detecting these spectral particles pushes technology to its limits. Experiments like Japan's Super Kamiok and use Olympic-sized tanks of ultra-pure water buried deep underground, waiting for the rare flash of light when a neutrino finally bumps into an atom. Other projects chase neutrinos beamed through Earth or trapped in Antarctic ice. Each capture is like finding a needle in a cosmic haystack, but every one carries secrets from the universe's most hidden corners. So the next time you feel nothing, remember, you're being constantly bombarded by the universe's most abundant, least understood particles. They're the silent witnesses to cosmic history, the invisible architects of stellar explosions, and perhaps the key to why anything exists at all. And they're everywhere, passing through you right now, unnoticed, like shadows of creation itself. Long before planets, stars, or even proper atoms existed, the universe took its first clumsy steps toward chemistry with a molecule so simple it seems almost laughable: helium hydride. Just a helium atom shackled to a single proton, this fragile pairing was the primordial handshake that kicked off molecular bonding in the cosmos. Formed when the universe was a mere 100,000 years old, still cooling from its trillion-degree infancy, this unassuming duo emerged in an environment so hostile it would vaporize modern stars like dew in a blast furnace. At that critical moment, temperatures had finally dropped enough for electrons to latch onto nuclei, forming the first stable hydrogen and helium atoms. But the cosmos was still pulsing with residual heat from the Big Bang, and in that seething aftermath, lonely protons began colliding with neutral helium atoms. These weren't gentle encounters, they were chaotic, high-speed crashes where only the strongest bonds survived. Most pairings shattered instantly, but a tiny fraction of helium and protons managed to cling together, creating the universe's first molecular marriage. It was a fleeting victory. As space continued expanding and cooling, these pioneer molecules were soon outcompeted by more stable hydrogen pairs, vanishing almost as quickly as they appeared. For decades, helium hydride existed only in theory, a ghostly relic predicted by quantum physics but never spotted in space. Then, in 2019, astronomers training the Stratospheric Observatory for Infrared Astronomy, a modified Boeing 747 packed with telescopes, finally caught its spectral fingerprint in a planetary nebula 3,000 light-years away. The discovery site was poetic, NGC 7027, a chaotic stellar graveyard where ultraviolet radiation from a dying star ripped apart molecules, mimicking the violent conditions of the early universe. There, amid the wreckage of a sun like star's final throes, helium hydride had briefly rekindled, offering scientists a time capsule to study chemistry's Big Bang debut. What makes this molecule so revolutionary isn't just its age, it's the role it played as cosmic matchmaker. Without it, the universe might have remained a featureless soup of monatomic gas. Helium hydride acted as a molecular catalyst, absorbing energy from collisions and re-radiating it as infrared light, helping the young cosmos shed heat faster. This cooling effect allowed denser clouds of gas to collapse, setting the stage for the first stars to ignite. In other words, this humble molecule was the spark that helped transition the universe from a smooth, hot plasma to the clumpy, structured cosmos we know today. Yet the detection nearly didn't happen. Helium hydride's faint signal hides at a specific infrared wavelength that Earth's atmosphere completely blocks. That's why scientists had to fly their telescope at 45,000 feet, above 99% of the water vapor that would have drowned out the signal. Even then, the telltale spectral line was whisper-thin, requiring painstaking analysis to confirm it wasn't noise. The discovery wasn't just a triumph of technology, It was a direct glimpse into the universe's chemical infancy, proving that our models of those first chaotic moments were correct all along. Now, researchers are hunting for even older traces of helium hydride, hoping to spot it in primordial gas clouds untouched by later star formation. Finding it there would be like stumbling upon a fossilized footprint from the dawn of time itself, a silent witness to the moment the universe graduated from nuclear physics to chemistry, setting in motion the chain of events that would eventually lead to planets, oceans, and life. And that's the real wonder. Every complex molecule in existence, from DNA to distant nebulas, owes its lineage to those first tentative bonds forged in the cosmic furnace. We've been taught since childhood that space has three dimensions: length, width, and height. But what if the universe itself is secretly flat? Not flat like a sheet of paper, but flat in the cosmic sense, meaning its geometry follows the rules we learned in high school math class. Parallel lines never meet, angles in triangles add up to exactly 180 degrees, and light travels in perfectly straight paths across unimaginable distances. This isn't just theoretical noodling, it's a conclusion drawn from some of the most precise measurements ever made, and it has staggering implications for whether the cosmos stretches on forever or eventually loops back on itself. The key to this cosmic geometry lesson lies in the afterglow of the Big Bang, the cosmic microwave background. When scientists mapped its faint temperature variations with satellites like Planck, they weren't just creating a baby picture of the universe, they were measuring its curvature. Here's how it works. If space were positively curved like the surface of a balloon, light rays would gradually converge, making distant objects appear larger than they are. Negative curvature, like a saddle, would warp light outward, shrinking distant objects. But the data revealed something startling. The universe's geometry is within a razor-thin margin of error, perfectly flat. Not slightly curved, not nearly flat, but mathematically, undeniably flat. That flatness isn't an accident. It's a direct consequence of inflation, the universe's explosive growth spurt in its first trillionth of a second. Imagine taking a crumpled sheet of aluminum foil and stretching it in all directions until every wrinkle smooths out. That's essentially what inflation did to space-time. It stretched any initial curvature so dramatically that the observable cosmos now appears flat, just as a small patch of Earth's surface seems flat to us despite the planet's roundness. But here's where things get mind-bending. A flat universe doesn't necessarily mean an infinite one. It could still be finite but unbounded, like a video game where leaving one edge of the screen brings you back to the opposite side. If you flew a spaceship straight ahead in such a universe, you might eventually return to your starting point, having circumnavigated the cosmos without ever encountering an edge. The catch: the universe would need to be staggeringly large for this to work without detectable repetition in the cosmic microwave background. Current observations suggest, if it's finite at all, the cosmos must be at least 250 times larger than the observable universe. The alternative, that space truly is infinite, raises its own dizzying questions. An infinite flat universe would mean there's no boundary, no outside, just an unending expanse where every possible configuration of matter repeats endlessly. Somewhere out there, an exact copy of you might be reading an identical script, while another version chose pizza instead of tacos for lunch. Infinite space guarantees infinite possibilities, but it also clashes with our intuition that everything, even the cosmos, ought to have a finite scale. Yet flatness isn't just about shape, it's tied to the universe's ultimate fate. A positively curved cosmos would eventually collapse in a big crunch, while a negatively curved one would expand forever at an accelerating rate. Flatness sits on the knife's edge between these fates, delicately balanced between expansion and collapse. That balance hinges on the universe's critical density, the precise amount of matter and energy needed to halt expansion but not reverse it after infinite time. Remarkably, our measurements suggest the cosmos hits this target almost exactly, with visible matter, and dark energy combining to produce the flat geometry we observe. So what's the verdict? The universe's flatness is one of cosmology's best established facts, but its implications are still wide open. Whether we're part of an infinite expanse or a vast but finite loop, the answer hides beyond the cosmic horizon, in realms whose light hasn't reached us yet. Until then, we're left tracing the geometry of the knowable, marveling at a universe that plays by Euclid's rules on the grandest possible scale. Black holes aren't just cosmic vacuum cleaners. They might be the universe's original ghosts, lurking unseen since the first moments of time. One of the boldest theories in modern cosmology suggests that dark matter, the invisible glue holding galaxies together, could actually be an army of primordial black holes forged in the chaos of the Big Bang. These aren't the black holes we know today, born from collapsing stars. These would be relics from the universe's infancy, when extreme density fluctuations could have squeezed pockets of matter into tiny, dense knots so tight they collapsed straight into black holes, some no heavier than an asteroid, others as massive as 1,000 suns. The idea isn't as far-fetched as it sounds. In the first second after the Big Bang, the cosmos was a seething, turbulent place where quantum fluctuations could have created regions of wildly different densities. Some patches might have been so dense that gravity overpowered all other forces, causing them to implode instantly. Unlike star-sized black holes, which take eons to form, these primordial ones would have appeared like cosmic snap freezes, tiny singularities popping into existence everywhere at once. And because they'd formed before stars or galaxies even existed, they'd have spent billions of years drifting unseen, clustering in halos around galaxies just as dark matter does. What makes this theory so compelling is how neatly it solves two puzzles at once. Dark matter's gravitational effects are undeniable. It bends light, sculpts galaxies, and holds clusters together, yet it refuses to interact with light or ordinary matter in any other way. Primordial black holes fit that description perfectly, massive enough to tug on stars and gas, but so compact and dark they'd be nearly impossible to spot. Even better, they wouldn't require any new, exotic particles beyond the known laws of physics. The universe could have cooked them up using nothing more than gravity and chaos. But there's a catch. If these black holes are out there, why haven't we detected them? Astronomers have hunted for them using gravitational microlensing, watching for the telltale warp in starlight as a black hole passes in front of a distant star. So far, the results are inconclusive. Too many small black holes would have left a blizzard of lensing events we don't see. Too many large ones would have disrupted star clusters or left X-ray signatures from gobbling up gas. The sweet spot, black holes around the mass of a planet, remains frustratingly elusive. Then there's the LIGO problem. When gravitational wave detectors started catching black hole mergers, some hoped these might be primordial relics colliding. But the colliding black holes detected so far are too heavy to fit most primordial models. Unless we find a population of smaller, quieter black holes, the theory hangs in limbo. Yet the hunt isn't over. New telescopes like the upcoming Vera Rubin Observatory could finally spot these shadowy suspects by catching their flickering distortions of background light. Others are searching for the ripples they'd leave in the cosmic microwave background or the subtle way they'd warp the apparent motion of stars. If even a fraction of dark matter turns out to be black holes, it would rewrite our understanding of the cosmos's structure and its origins. The implications are staggering. If confirmed, it would mean the universe's dark scaffolding isn't made of some mysterious particle, but of gravitational potholes left over from creation itself. These black holes would be cosmic time capsules, untouched since the first second of existence, carrying secrets about conditions so extreme they defy reproduction even in our most powerful colliders. And lurking unseen, they'd be proof that sometimes the universe's most profound mysteries aren't written in particles or energy, but in the silent pull of ancient, invisible knots in spacetime. The idea of a multiverse, countless parallel universes bubbling beyond our own, might sound like science fiction, but its roots dig deep into the bedrock of modern physics. It doesn't spring from wild speculation. It emerges as a natural consequence of two of our most powerful theories: cosmic inflation and quantum mechanics. Picture the early universe not as a single, uniform explosion, but as a roiling sea of energy where quantum fluctuations danced at the smallest scales. Inflation, that brief but violent expansion spurt, didn't just stretch the cosmos, it magnified those tiny quantum ripples into cosmic proportions, seeding the galaxies we see today. But here's the twist: if inflation could happen here, why not elsewhere? Quantum mechanics tells us that empty space isn't truly empty. It's a frothing, bubbling foam where particles flicker in and out of existence, borrowing energy from the vacuum itself. In the chaotic aftermath of the Big Bang, this quantum uncertainty might have triggered inflation in multiple regions simultaneously, each patch expanding into its own separate universe with its own unique physics. Like soap bubbles in a sink, these bubble universes could have nucleated endlessly, each one pinching off from the others, forever out of reach. Our observable cosmos might just be one bubble in an infinite cosmic froth, floating alongside others where the laws of physics, the strength of gravity, the mass of electrons, even the number of dimensions, are completely different. The math behind this is startlingly elegant. Inflationary models don't just allow for multiple universes, they practically demand them. Once inflation starts, it's notoriously hard to stop. Quantum fluctuations can create pockets where inflation ends, forming stable universes like ours, while the surrounding space continues expanding exponentially, birthing new bubbles ad infinitum. This eternal inflation scenario suggests a multiverse that's not just vast but infinite, with universes emerging endlessly, each one a self-contained reality with its own history, its own stars, and maybe even its own versions of us. Critics argue this is untestable metaphysics, but supporters point to subtle clues. If our universe collided with another bubble long ago, the crash might have left scars in the cosmic microwave background, anomalies in the radiation's temperature patterns. Some researchers claim to have spotted such signatures, though the evidence remains controversial. Others suggest that the unexplained values of fundamental constants, why gravity is so weak compared to electromagnetism, for instance, might find answers in a multiverse where every possible combination plays out somewhere. The implications are dizzying. In an infinite multiverse, every conceivable outcome happens somewhere. Universes where life never emerged, universes where time runs backward. Even universes nearly identical to ours, where every choice you didn't make plays out in another reality. It's a vision of existence so vast it makes the observable cosmos feel like a single grain of sand on an endless beach. Yet for all its grandeur, the multiverse isn't a proven fact, it's a compelling prediction, a shadow cast by the mathematics of inflation and quantum theory. Whether it's real or just a beautiful idea, one thing's certain: the universe's origins might be far stranger and far more crowded than we ever imagined. The early universe wasn't just a silent explosion, it was a roaring concert, a cacophony of pressure waves rippling through the searing plasma like sound through water. These weren't ordinary sound waves, they were Barrian acoustic oscillations, massive vibrations where regions of compressed gas and rarefied emptiness pulsed outward at half the speed of light. Picture dropping a stone into a pond, but instead of gentle ripples, imagine tsunamis of matter and energy racing across the cosmos, leaving behind a frozen record of their passage, one we can still read in the positions of galaxies today. These cosmic sound waves began when the universe was a dense, scorching soup of particles. photons and electrons were locked in a furious dance, with radiation exerting immense pressure on the plasma, resisting gravity's pull. As the universe expanded, gravity would compress the gas, while radiation would push back, creating oscillations, regions of compression and rarefaction that stretched for hundreds of thousands of light years. But when the universe cooled enough for atoms to form, radiation and matter decoupled, and those waves suddenly froze in place like footprints in drying cement. The result, a vast three-dimensional pattern where galaxies today are slightly more likely to be found at specific distances from each other, a relic of those primordial vibrations. Astronomers call this the cosmic ruler. By measuring the preferred spacing between galaxies about 500 million light-years, scientists can trace the universe's expansion history with astonishing precision. It's as if the cosmos handed us a standardized measuring tape stretching back to its infancy. The Sloan Digital Sky Survey, mapping millions of galaxies, revealed this faint but unmistakable imprint: concentric shells of galaxy clustering, echoing those ancient pressure waves like rings in a tree trunk marking its growth. What's extraordinary is how long this signal endured. For nearly 14 billion years, through the birth of stars, the collision of galaxies, and the relentless expansion of space, that acoustic fingerprint remained intact. The galaxies we see today didn't form randomly. They were born from the crests and troughs of those waves, a cosmic rhythm guiding where matter would eventually clump. Even dark matter, invisible and elusive, was pulled into this symphony, its gravitational influence amplifying the pattern. The analogy isn't poetic license, it's physics. Those oscillations weren't just visual, they were literal sound waves with frequencies so low they'd be 57 octaves below human hearing. If we could listen to the early universe, it would sound like a deep, resonant hum, a bass note reverberating through creation. And while the sound itself faded eons ago, its impact is etched into the universe's structure, a silent song written in the positions of galaxies. This discovery didn't just confirm theories of the Big Bang, it gave us a new tool to probe dark energy. By comparing the ancient ruler's size to its modern counterpart, astronomers found that the universe's expansion is accelerating, driven by that mysterious force we still struggle to understand. The wave's spacing acts like a yardstick bent by time, revealing how space itself has stretched over eons. Yet for all its precision, the cosmic symphony raises new questions. Why did certain wavelengths dominate? Could there be even older, fainter harmonies hidden in the void? Future telescopes, like the Euclid Space Observatory, aim to map these oscillations with even finer detail, potentially uncovering clues about inflation, dark matter, and whether our universe is truly alone. So next time you see a star map or a simulation of galaxy clusters, remember, you're not just looking at points of light. You're seeing the fossilized echoes of a universe ringing like a bell, its deepest vibrations still shaping everything we know. Think of the early universe as a grand stage where particles raced around at light speed, weightless and free, until the Higgs field switched on like a cosmic dimmer, suddenly slowing them down with the gift of mass. This wasn't instantaneous. For the first fraction of a second after the Big Bang, the Higgs field, the invisible energy blanket that permeates all of space, was dormant, drowned out by the universe's extreme heat. Particles like quarks and electrons behaved like photons, zipping around without resistance. Then, as temperatures cooled below 100 trillion degrees, the Higgs field awoke, snapping into dominance like a phase transition between water and ice. In that critical moment, the laws of physics as we know them were born. This delay had staggering consequences. Without mass, the universe's earliest particles couldn't clump together to form atoms, much less stars or planets. The Higgs field's late arrival meant that for a fleeting instant, the cosmos was a frictionless playground where forces like electromagnetism and the weak nuclear force were indistinguishable, merged into a single, unified interaction. Only when the Higgs kicked in did these forces split, giving rise to the diversity of physics we see today. It's as if the universe spent its infancy in a featureless fog, then suddenly crystallized into structure. The timing was precise, almost suspiciously so. Had the Higgs field turned on earlier, particles would have grown massive too soon, stifling the universe's expansion and leaving it a dense, sluggish soup. Too late, and matter might never have coalesced at all, with particles too lightweight to bind. This fine-tuning raises profound questions. Was this a lucky accident, or does it hint at deeper laws we've yet to uncover? Some theories suggest the Higgs itself might be a cosmic relic, its behavior frozen into place by interactions with even earlier, now vanished fields. Discovering the Higgs boson in 2012 at the Large Hadron Collider wasn't just about confirming a particle, it was a window into that pivotal moment when the universe chose its rules. The boson isn't just another particle, it's a ripple in the Higgs field, proof that this energy tapestry exists. Experiments now aim to measure the Higgs properties with exquisite precision, hunting for clues about why it behaves the way it does. Tiny deviations from predictions could point to new physics, perhaps even connections to dark matter or hidden dimensions. What's haunting is how delicate this all seems. The Higgs field strength determines the masses of electrons, quarks, and by extension, the size of atoms and the stability of stars. Alter its value even slightly, and chemistry as we know it collapses. In a multiverse of infinite possibilities, our universe's Higgs might be the rare ticket that allows complexity and life to exist. So the next time you feel the weight of an object in your hand, remember, you're sensing an echo of that cosmic transition, a split-second decision the universe made before time itself had fully settled into its rhythm. The cosmic microwave background, the oldest light in the universe, wasn't always the faint microwave whisper we detect today. 13.8 billion years ago, it blazed across the cosmos as searing, visible light, bright enough to outshine every star in the sky combined. But the relentless expansion of space has stretched those once vibrant photons into the microwave equivalent of a dim glow, like a once roaring fire reduced to embers. This transformation didn't just dim the light, it rewrote its entire identity, shifting its wavelength thousands of times longer than when it first escaped the primordial plasma. Imagine holding a rubber band taut and plucking it to create a high-pitched note. Now stretch that band until it's nearly sagging. The sound deepens, the frequency drops. That's precisely what happened to the universe's first light. As space expanded, the photons traveling through it were stretched, their wavelengths growing longer and energy fading. What began as blinding white light, hotter than the surface of the sun, gradually shifted to red, then infrared, and finally into the microwave realm where we detect it today. This process, called redshift, isn't just a historical curiosity, it's an ongoing transformation. Every second, as the universe grows larger, those ancient photons stretch a little more, inching toward even lower energies. Here's the haunting part: this light won't just fade, it will eventually vanish from view entirely. In another 100 billion years or so, the cosmic microwave background's wavelength will stretch so far that it becomes undetectable even to our most sensitive instruments. The afterglow of the Big Bang, our most direct link to the universe's birth, will slip beyond the horizon of observation like a ship disappearing over the edge of the world. Future astronomers born in galaxies so distant their light hasn't yet reached us might look up at a night sky devoid of this crucial evidence, left to piece together cosmic history without its oldest witness. But the story gets even stranger. As dark energy accelerates the universe's expansion, distant galaxies will redshift so dramatically that their light stretches beyond detectability. The night sky of the far future may contain only the dim glow of nearby stars, with no trace of the cosmic microwave background or the billions of galaxies we see today. Civilizations arising in that era could reasonably conclude the universe is static and small, with no evidence of a Big Bang or an expanding cosmos. the greatest discoveries of modern cosmology, inflation, dark energy, the universe's age, might become impossible to verify, buried under the weight of an accelerating void. This raises a chilling possibility. We might be living in a uniquely privileged moment, a cosmic sweet spot where the afterglow of creation is still visible but stretched just enough to study. It's as if the universe handed us a fading love letter from its infancy, one that future generations might never get to read. And that's the ultimate irony. The very expansion that allowed galaxies, stars, and life to form will one day erase the evidence of how it all began, leaving the universe's greatest secrets hidden in plain sight, yet forever out of reach. What if the Big Bang wasn't the beginning, just a doorway? One of the most radical theories in cosmology suggests our entire universe might be the interior of a black hole in a higher dimensional reality. This isn't just sci-fi speculation. It's a serious hypothesis that could explain the universe's birth, its expansion, and even the strange fine-tuning of physical laws. The idea hinges on a startling parallel. The mathematics describing the collapse of a black hole in four-dimensional space eerily resemble the equations for an expanding three-dimensional universe like ours. Picture a black hole in a higher dimensional parent universe. When matter collapses into it, the event horizon, the point of no return, forms a boundary that, from our perspective, looks like the Big Bang. Inside, the infalling material doesn't just vanish, it gets stretched and repurposed, inflating into an entirely new spacetime, our cosmos. In this view, the singularity at a black hole's heart isn't a dead end but a bridge, a cosmic reset button that spawns a self-contained universe with its own physics. The expansion we observe today, that's the continued stretching of space as matter and energy rain down from the parent universe's collapse, feeding our growth from the outside in. This theory elegantly solves two puzzles at once. First, it explains the universe's inexplicably low entropy at the Big Bang, a state so ordered it's like finding a library with every book perfectly alphabetized. Black holes naturally maximize entropy, so if ours began as one, it would have started with a clean, low-entropy slate. Second, it offers a potential origin for the laws of physics themselves. Just as water freezes into ice with different crystal structures, the frozen remains of the parent black hole's collapse could have locked in specific symmetries and constants, like the speed of light or the strength of gravity. The implications get wilder. If our universe is a black hole, there might be others, countless nested cosmoses, each with different physical laws branching off from their own parent collapses. Some could harbor exotic physics where time runs backward or gravity repels. Others might be stillborn, collapsing instantly under incompatible rules. This cosmic Darwinism could explain why our universe seems so finely tuned for life. Only the habitable black hole universes would contain observers to notice. Critics argue the theory is untestable, but subtle signatures might lurk in gravitational waves or the cosmic microwave background anisotropies that betray our cosmic parentage. Others suggest the holographic principle, where our 3D universe is encoded on a 2D boundary, aligns perfectly with this idea, since black holes store information on their event horizons. Whether true or not, the hypothesis forces us to rethink reality's architecture. If correct, the night sky isn't just a window to distant stars, it's the shimmering inner wall of a gravitational tomb, a universe within a universe echoing the infinite. From the universe's unimaginable birth in a trillion-degree furnace to the eerie possibility that we might be living inside a black hole, every revelation peels back another layer of cosmic mystery. We've traveled through time dilation in the infant cosmos, witnessed ghostly neutrinos that outnumber atoms, and stood in awe of the delicate fine-tuning that allowed galaxies and us to exist. Yet for all we've uncovered, the most humbling truth is how much remains hidden. Dark energy's accelerating grip, the true nature of dark matter, even the question of what, if anything, came before the Big Bang. These are puzzles that keep scientists awake at night. Think about this. Every answer we've found only reveals deeper questions. The cosmic microwave background, once thought to be the final answer to the universe's origins, turned out to be just the opening chapter. The Higgs field, praised as the final piece of the Standard Model, now hints at undiscovered physics and those primordial gravitational waves we've yet to detect. They could rewrite the story of inflation itself. The universe isn't just stranger than we imagine, it's stranger than we can imagine, constantly defying our expectations. Here's what's truly exhilarating. You are part of this story. Every atom in your body was forged in the hearts of stars, shaped by quantum fluctuations from the universe's first second. When you look up at the night sky, you're not just observing history, you're living it, a conscious fragment of the cosmos trying to understand itself. And that's the real gift of these mysteries. They're an invitation to stay curious, to question, and to revel in the fact that we're surrounded by wonders we're only beginning to grasp. So tell us, which fact made your jaw drop the hardest? Was it the holographic universe theory or the cosmic scent of burnt toast? Drop your favorite in the comments, and if you're hungry for more mind-bending revelations, hit subscribe and ring the bell. The universe has spent 14 billion years hiding its secrets. Together, let's uncover